Hello and welcome to the second in a series of 3 films about the higher level equilibrium topic. In the standard level topic we looked at what equilibrium constants were and we wrote expressions for them. Here we're actually going to be trying to calculate the value of K, which we didn't have to do at SL, and we're also going to decide what units it might have. Okay, it's hopefully going to be a bit of a shorter film than the last one. That was a bit long, but we will start with a reminder of how you write an equilibrium constant expression. So for any equilibrium where we've got reactants and products, the products are on the top and the reactants are on the bottom. And if we've got more than one reactant or product, then we multiply them. And if we've got some numbers in our equation, so that is stoichiometric coefficients, then they will appear in our equilibrium constant as powers. Now, hopefully that's all okay. That was standard level stuff. Now we're going to look at deciding what units K has. Now, there are different types of K, and they're called Kc and Kp, depending on whether you're talking about things in terms of concentrations or pressures, but we're only interested in Kc in the IB course. So in other words, all the things that we look at are going to be concentrations and not pressures. So in other words, the terms in our equilibrium constants will always have units of moles per dm cubed, because the concentration of a substance, remember square brackets of concentration, is always given in moles per dm cubed. You can have other units, but they're the ones that we normally use. Right, now in that case, what units is K going to have here? Well, it's going to have moles per dm cubed divided by moles per dm cubed. Remember, we're just doing the units here. We're not putting any numbers in. We're just talking about the units. And that unit's going to cancel with that one. So in this case, K has no units. Okay? In this case, we've got moles per dm cubed divided by 2 mole per dm cubed terms, times moles per dm cubed, and although those cancel, we're left with this, so this is now 1 over moles per dm cubed, and that is the same as saying moles to the minus 1 dm cubed, not per dm cubed anymore, but dm cubed. Now hopefully your maths is up to that. Okay, it's not very complicated maths, which is good, because my maths isn't that good, but I can say to myself that 1 over something basically changes the sign of the powers. Okay, so hopefully your maths is up to that. If it's not, then I suggest you practice your laws of indices a little bit. But anyway, now we've got another K where we've got 4 concentration terms on top. So this would be like moles to the power 4 dm to the minus 12 on top, right? On the bottom, we've got a squared concentration term, so moles squared dm to the minus 6. And they will cancel with 2 of those, and they will cancel with 6 of them. And so my units for K in this case will be moles squared dm to the minus 6. Now, as I say, there is some simple maths involved there. If you're not up to the maths, you can just remember what the units will be based on how many terms there are top and bottom. But we're not going to go through that kind of a thing in this film because it's quite an inefficient way of doing things. If you do want to ask me how it's done, then go ahead and ask, but we're not going to cover it in this film. Anyway, now let's have a look at finding the value of K. Remember, this is not something we had to do in the SL course, but we do have to do it in HL. Now, first thing we're always going to have to do is write an expression for the equilibrium constant, and in this case that's going to be the concentration of HI, because that's the product, and we're going to square it, okay, because there's 2 of them, and in the reactants we're going to have the concentration of H2 multiplied by the concentration of I2. And we're given all the numbers that we need for this, right? We've got the concentration of H2 and I2 and HI as well. So let's just plug those numbers in, okay? So that is going to equal 1.695 times 10 to the minus 2, and that's going to be squared. And we're going to divide that by 2.484 times 10 to the minus 3, multiplied by 2.514 times 10 to the minus 3. And if you do the maths there, then you end up with a number of 46. Now, what units does this have? Well, there are 2 concentration terms on top, because it's squared. There's 2 on the bottom, so they all cancel, and this number will have no units. Now, I suppose that's the simplest kind of find the value of k problem, because we're given all the concentrations already. Sometimes you won't be given the concentrations. We've got to do a little bit more work. Believe it or not, this is exactly the same problem as before. I've just changed a little bit of it, in the sense that I'm not giving you concentrations anymore. I'm giving you the masses of the substances. Okay, and I've also given you a volume of the vessel. Why is it that I've done that? Well, because you want to write your equilibrium constant, which is HI squared over H2 times I2, or the concentration of H2 multiplied by the concentration of I2. So in order to do this, you're going to have concentrations in there, but you don't. You've got masses. What does that mean? Well, if we want things in moles per dm cubed, values in moles per dm cubed to put into our fraction here, then we're going to have to turn these masses into moles. And remember, the number of moles is equal to the mass divided by the molar mass. And what is more, concentration is equal to number of moles divided by volume. And we've got a volume here. Okay, so once we've found the number of moles of each of these, if we divide it by 2, because that's the volume, then we'll have the number of moles per dm cubed. Okay, this is all kind of stuff from the moles calculation, which you might have done quite a long time, from the mole calculations topic, or from the quantitative chemistry topic, which you might have done quite a while ago. But anyway, it's important to understand it. Okay, so let's just do that for one of these. I could do it for all of them, but let's find the number of moles of hydrogen. So that's 0.01002 divided by 2.016 for the molar mass, because it's H2. Okay, and that gives me a value of about 4.97 times 10 to the minus 3. And if I divide that by 2, then the concentration of H2, oops, I've written I2 there, the concentration of H2 is that over 2, and that is 2.485 times 10 to the minus 3, which, if you look at the previous slide, you can see that's the same concentration that I gave you before. And if you do that for every one of these substances, then you'll end up with the same concentrations you had before, and you should end up with the same value of the equilibrium constant. But it might be worth just checking that you can do that before you move on. Now, a similar problem but slightly different. We've now got the same masses, right? And we've got the volume, but we're not given the mass of hydrogen iodide. Okay, we are, however, given the value of K, right? So in other words, we know now, as soon as we've written our equilibrium constant, okay, that is HI squared over all the rest of it, H squared times I2, H2. Oh, I've lost the power of writing. Okay, so H2 multiplied by I2. We're now trying to find the mass of HI. Okay, so we know that 46 equals the concentration of HI squared over 2 values that we can find the way we found them before, which means that we can just rearrange this, hopefully, and find that the concentration of HI is equal to the square root of 46 multiplied by these 2 values. Okay, blah blah blah. And then we know the concentration of HI. We know that the concentration is the number of moles divided by the volume. So we know that this value which we've just found, if we multiply that by the volume, we'll have the number of moles. And now that we know the number of moles, we can multiply that by the molar mass of hydrogen iodide, and we will know the mass. Okay, so once again, I'm not going through that whole calculation, partly because it won't fit on my slide, but partly because it's basically fairly simple stuff from the quantitative chemistry topic. Might be worth checking that you can do it and that you get the same mass that you had before, because this is exactly the same problem. I've just rearranged the numbers slightly. Okay, but that's about it, really. Hopefully you've understood what we did there. Hopefully you had a chance to just stop and check that you could do all the calculations, right? As I say, the problem didn't change, so the second time we did it, you should have ended up with exactly the same value of the equilibrium constant as you did before. But do have a go at the calculations, and do come and see me if you've got any problems, or do post a comment on YouTube if you've got any comments or questions.